yeah, I won't present you any fancy finite element model, but today I will rather show you I use FEniCS to implement a finite pressure anisotropic hyperelasticity model. The plan is pretty simple. The first question is why? Why do we need a dedicated model for shock physics applications? The second question is how did we build a special model for this application? And so what? Did we find anything good or not? I will talk about continuum mechanics, of course. I will try to explain you a specific constitutive law, which is a relation between the stress, the displacement, and the temperature. I will focus on the mesoscopic scale, which means that I will zoom on my materials, and I will try to find a constitutive law for the grains, which are highly anisotropic, even in materials. And I will focus on elasticity, but finite-strain elasticity, which means that I won't talk about our dearly beloved epsilon linearized strain tensor. I will rely on three hypotheses, which are written here, from which you can derive the constitutive laws. When you apply thermodynamics, you can find that either the first Euler-Kirchhoff stress tensor or the second one is the derivative of the free energy with respect to a strain measure. So the only thing to understand is when you're dealing with elasticity, the only thing you need is the expression of the energy with respect to the strain. And when the strain is small, it's pretty straightforward. You can replace a unknown function by its second order Taylor expansion, and you get the linear hyperelasticity models. But when the strain is not small, the main way to deal with it is to replace your function by another one which relies on the invariance of your strain tensor. And when you are fully anisotropic, you have to introduce cross invariance between the strain and your structural tensor. But there is no clear full expression when the strain is big and when you have a highly anisotropic model. So the main question is, what can you do to model elasticity of an anisotropic media when the strain is so small, but with a high pressure and a low deviatoric stress? Why would I say low deviatoric stress? Because when you have a very, very high pressure, it won't necessarily trigger any inelastic mechanism such as plasticity, because when you look at lattice, either it's perfect or with dislocation, and when you compress it, it won't break bonds and it won't make the dislocation move. So as an example, when you think about plasticity, most of the time the input of the plasticity model is shear stress, which means that you can have a very, very high pressure, very high elastic deformation because of pressure, but you have a low deviatoric stress because it's bounded by plasticity. So some colleagues from Los Alamos tried to figure out what is the expression of the tangent shear modulus with respect to pressure. And they found out that when you compress a material, it's stiffened, but with a strange way. Sometimes you have different direction with anisotropic materials, and they do not stiffen the same way. You cannot use linearized elasticity because you have pressure dependence coefficients, and you cannot use incremental approach because you will lose thermodynamic consistency. So the main goal of the presentation is to show you how did we build a model for this specific application when you have a huge shock wave with a high pressure, but you have a low deviatoric stress because of plasticity. So the key idea was to say that the transformation can be seen as two successive decomposition. The first one, a big one, because of pressure, and you have a small deviation from this compressed state. So you can introduce a strain which measures the deviation relative to a pre-compressed state. And it's a fancy feature of the model because the strain measure that you will use in your constitutive laws depends on the materials. Each materials have a different strain measure to measure the deformation. And the parameter which is small is heat yield, which is the deviation from the compressed state. And we reused the idea behind the Hooke's law, which means we expanded the free energy with respect to heat yield, and not just E, because E is not small anymore. So the linear term is 0 for an argument. So you have to calibrate three things. You have to identify what's the energy under pure compression, which can be measured if you're using, for instance, Diamond and cells, which can measure pressure, and you integrate this relation and you get the energy over pure compression. You have to determine how does the lattice compress under pure pressure. Then you have to track three lengths and three angles. and you have to determine the isochoric stiffness tensor, which is the stiffness of the materials under pure compression and small shear. And why did we use FEniCS for it? Because when you identify all these things, you just have to use UFL derivative to get the stress function, and you can do it twice to get the tangent stiffness. And I assure you, it's really evil to derive by hand. So we tried it on copper because it's a very, very well-known materials. So we choose a Vinny equation of state for the pressure, and for the copper, which is a cubic material, it's pretty simple because when you apply a uniform pressure on copper, you get an isotropic response. So F0 is just multiplied by the identity. And you have two isochoric shear modulus to calibrate, and we found some data from Los Alamos, again, at the grain scale to fit the shear modulus of the one crystal. And then we did a numerical homogenization because we wanted to find what's the macroscopic shear modulus of a polycrystal of copper. So we compressed it and we shared it, and that's where we used FEniCS. We had a kind of small mesh with only 200 grains, but we performed a lot of simulations with various crystallographic and a lot of distribution. We applied a macroscopic gradient of transformation, and we shared it. And we were looking for the periodic fluctuation of the displacement field for it. We applied periodic boundary condition, and of course, for the solver, you used FEniCSx for the variational formulation. And we also used Dolphinix multiple constraints for the periodic boundary condition. Yeah. So we did it. We were expected to have a great error because we were fitting our data on a single crystal grain, and we were expecting to find some shear modulus at the macroscopic scale. And it was striking because we found the yellow curve for the dependence of the shear modulus over pressure. It can be multiplied by a factor 10. And what's strikingly impressive in this curve is the blue one and the other one in blue are two widely modeled used in shock physics, which are calibrated against macroscopic data. Whereas our approach in the yellow curve was to fit everything at the grain scale and to homogenize it to get the response at the macroscopic levels. Yeah, we also did it for lower symmetry crystals, typically on panthrite, which is an explosive materials. And we found that the shear modulus with respect to the pressure evolves between the void bond and the raised bond. And of course, for obvious reason, you cannot do experimental studies on it because it will burst the laboratory. And we also did it on exogen, which is another explosive materials with a lower symmetries. And we also found that the shear modulus is consistent with the void bond and the raised bond. So what are the perspectives? We want to apply this methodology for lower symmetry crystals, typically HMX, which is monoclinic, and TRTB, which is triclinic. We also want to extend this model to finite temperature, because when you have a huge shock wave, you can have a huge pressure, but it also raises the temperature with a very, very significant temperature. And we are also planning to couple this to inelastic phenomena such as plasticity and twinning to get a full idea of what's the constitutive laws of polycrystals. So yeah, are there any questions?
Thank you, Paul. Any questions? Yes.
Thank you, Paul, for this nice presentation. It was very, very nice, beautiful. So you mentioned that there is some stochastic source that you have several samples of your polycrystal geometry.
Yep.
What is this stochasticity? Where does it come from?
Because when we did numerical homogenizations, we had very few grains because I wanted to run very fast on the laptop. So 200 grains is not very representative of truly crystals. But I saw some papers saying that you can have a very, very small sample, and as long as you run a lot of simulations with different orientation, you get, on average, a great representation of the shear modulus.
But how do you model this randomness.
Or just running Neper, generating polycrystals with different seed. So I have different grains, different orientations, and I was running simulation on it.
Yes.
But you still have to compute one large example in order to check if you have a systematic bias. So this statistical volume element, they work, but you have to be sure then that the large number delivers the same response as a really larger single one. And you have to check that once.
I mean, you mean convergence with respect to the elements or with respect to a big model?
The model size, yeah, so number of inclusions, heterogeneities that you have in your model.
I have no inclusions here. I have no inclusions, it's just...
But you have a polycrystal.
Yep.
So essentially you have like, every crystal has a different orientation.
Yep.
Yeah, so you can call that, not an inclusion, but a heterogeneity.
Hmm.
Yeah, and you need to check that once.
Yep. And we did not did it.
Yes. Now.
Maybe just out of curiosity, which I didn't quite understand. I mean, the shear modulus, isn't it sort of a material parameter that sort of depends on the deformation, and where there is also a closed expression for it, depending on the strain energy density function? Because you sort of measure the shear modulus, right? I mean, isn't it sort of a closed form depending on the strain energy function you have?
Is there any closed form for the shear modulus?
Linear elasticity.
In linear elasticity, yes, but
It also mean for just had this Holtz of the book open. I mean, for example, for a generalized Neo-Hookean model, there's also sort of an expression for the shear modulus that depends on the first invariant, for example.
Yep. Yeah. In fact, when you are dealing with linear elasticity, the shear modulus is a constant. You know, and
in your realm, that it's deformation dependent, but there are also, at least for some strain energy functions, analytical expressions for it.
I don't know if there's an analytical expression for any class of anisotropy, because this model works for anything. I was trying to find some way to apply the invariance approach for this model, but when you get low symmetry crystals, your structural tensor can be order 4, order 6, and it's very, very hard to split the invariance, which some of them rely on pressure and some of them don't. And I didn't find anything. Invariance works very well for isotropics, transverse isotropy, orthotropy. But when you're dealing with monoclinic crystals, it's you have a very, very large set of invariants, and you cannot find any shear modulus.
Okay, if there's no more questions, thank you again, Paul.